Okay, so we have one more example to finish in the growth and decay section. 6.5. So we're going to talk about interest compounded continuously. So we know the compound interest formula. Do you know the compound interest formula? What does that say? Let's say I'm measuring a value of the balance in an account, P. It starts out with an initial principal of P naught. What do you multiply by to talk about compound interest? Say compounded n times per year.
Isn't it 1 plus 1 over n being the number of compounding periods?
Well, technically it's R over n.
Right.
Right, where R would be the interest rate.
Right.
Yeah, times.
1 over n?
NT.
Well, it's NT. I'm talking about the generic formula, not applying any calculus or anything. Okay, so now if we let n approach infinity, right? This is what compounded continuously means. Continuously means at every infinitesimal fraction of time, right? No matter how small you dice up the number of times they're compounding, you can do it more, right? So as n goes to infinity, this leads us to look at the limit as n goes to infinity of this guy, which we can actually write as this guy, 1 plus r over n to the n to the t. Now it turns out you can show that this limit in here goes to e to the r. Right? We saw that when this was 1 it went to e. That's because here it gives you the power of the e. And I can justify that for you a little bit later if we want. When we talk about indeterminate forms and finding, we're going to go over limits again and talk about some new limit techniques, but you'll see that that gives you e. But you'll notice that this is just that p naught e to the rt formula. Right, same PERT formula that will give us that here. So this means that compounded continuously is the same as exponential growth. And so if we want to come up with this theoretical situation, because really in real life you won't have something like this, but theoretically it might be useful to consider things like this. We can talk about exponential growth, and we can study this kind of situation in exponential growth when things are just going crazy. Okay, and that leads us to example 4 in the handout. Okay. So I call it a mythical bank because no bank's going to pay 5% interest these days. Okay, so a bank pays 5% interest compounded continuously. Suppose you deposit $4,000 into this bank. A, write down a differential equation together with an initial condition whose solution gives you the amount in your account at any time t. So what are we given? We're given the interest rate. So we're given the r value. How would you write that down here?
0.05.
Right, 0.05. That's just the interest rate as a decimal percentage. Right? You write it the percentage in decimal. We also know the initial amount that you invested is $4,000. We see the phrase compounded continuously in the continuously. This means exponential growth, which in turn means the formulas in the top box are the ones that apply. Right? So now if you go to A, it asks for the differential equation with initial condition. Right? And so what is that here? That's just P prime equals RP, that's the differential equation. The initial condition is an equation that tells you what your initial starting point is. So this here is called the differential equation. Class that you guys might study later on, and this is called the initial condition. Right, so we're not going to do too much on differential equations here because there's an entire class devoted to this, and it's actually going to be useful for most of you because a lot of you, I know some of you in here are math majors, but some of you are also in chemistry majors. When you're doing a course like physical chemistry, understanding differential equations is going to be very important. So it's probably a good idea for you to take that, even if your major doesn't officially require it. And it's not that difficult a class. It's definitely, it's about, I would think, at the same level of Calculus 2, even though it's kind of above, but it'll have a Calculus 2 feel to it. Yeah, so anyway, so in part A, we're just literally going to plug the numbers into this formula. So the differential equation is going to be P prime equals 0.05P. The initial condition is just going to be P of 0 equals 4,000. And that's it, you just write that down. So it didn't ask you to do anything with it. At what rate in dollars per year is your account increasing when the balance reaches 6,000? Well, we know P is equal to 0.05. It's P. So this here is your rate of growth. P here represents your current balance, of course. So the answer here is simply going to be, what is the rate of growth? Technically, I want to put a T. This is just going to be 0.05 times 6,000. Whatever that is. So that's not a big deal. The last part is going to take a little bit of work to set up. Well, not really. How long does it take to reach 5,000? Okay, so this one here is asking for time. How long? So we obviously need to use an equation that has time in it. So this equation won't apply. I have to use another equation. What equation do you want to use? What's the equation I'm using?
Would it be P naught ERT?
Yeah, P equals P naught e to the RT. This is an equation that it has time in it, so I can solve for time. And I kind of know everything else. So I know what I want the balance to be. I want it to be 5,000, so I'm going to put 5,000 here. I know I started out with 4,000, so I'm trying to figure out if I deposit 4,000 today, how long will it take to get to 5,000? E to the R, I know what R is, that's 0.05 times T. And so now I want to solve for T. This means we can start solving that. So that's 5 divided by 4 is equal to e to the 0.05t. This means that ln of 5 over 4 is equal to 0.05t. This means your t is equal to ln of 5 over 4 times 20. And whatever that is. So that's that. That ends this section. In the grand scheme of things, it's not a very bad section. Most things you do will be a lot more difficult than this. So as for the next thing, we're going to go revisit trig, and we're going to learn about some rules for trig functions. Well, for the trig functions, you actually already kind of know a lot of the stuff, like the derivative of sine and cosine and tangent. But we really want to get to inverse functions, as well as later on down the road, we're going to be doing a topic that's called polar coordinates, where you're sort of going to come up with a new coordinate system instead of the xy coordinate system that might be beneficial in certain circumstances. And so really remembering your trig is going to be important. So I think I want to just make sure I do a trig review. So this might be boring to death to some of you, but it's necessary to understand.
Sorry, how come for above there you have to like define that P0 is 4,000 if P isn't necessarily in the differential equation where we start?
Oh, that's a different thing. This equation here is called the initial condition. So
Okay.
that's the purpose of this equation, to tell me what is the starting point.
Oh, okay, but it doesn't necessarily have to feature in the differential equation?
No, not necessarily.
Okay, alright.
So the thing is with that, without this information, you'll have unknowns in the general equation. Like you won't be able to figure everything out. Like you wouldn't be able to figure out this number here,
Okay.
unless for some reason you were given. Okay. So we're going to talk about a trig review. So we're going to need to remember about what these trig functions are, SOHCAHTOA, all that stuff, how to graph certain trig functions and transformations. We're going to need to know what is the value of the trig functions at the special angles. We're going to need to remember all students take calculus, all that good stuff. So let's start. The stars of trig are basically the functions sine and cosine. Right? So we can remind ourselves of what those guys are. On the unit circle, if you make an angle with the positive x-axis, call that theta, and you shoot a line out from the origin to hit the circle, sine and cosine are the numbers that give you the coordinates of this point. So cosine of theta will give you the x-coordinate at that point, sine of theta will give you the y-coordinate at that point. From this, so from this you can also extend, well maybe I'll talk about SOHCAHTOA later. So here we can create a right triangle. So you can go on this circle, in this setup, and you can kind of connect the triangle here. Right? You can make a right triangle. Right? And we know a lot of things about the right triangle. For example, we know Pythagorean theorem applies to a right triangle. This means that we can obtain this right triangle where the x distance is actually the cosine of theta, and the y distance is actually the sine of theta, and this is 1. And so we can get that cosine squared plus sine squared equals 1. This is called the Pythagorean identity. You're expected to remember that. There will be multiple occasions on which you have to apply this identity by either solving for sine or cosine, or solving for sine squared or cosine squared. It will come up all the time. What else we can do is, using similar triangles, we can sort of take our little triangle that we've created that has length 1 and extend it to a triangle that has hypotenuse r. This length here is cosine, and that length here is sine, and this guy here is the x, and this guy all over here, this guy here is the x, and that guy here is the y. You can come up with an equation by applying the similar triangles formula. Right, so the similar triangle says the ratio of corresponding side lengths are equal. So from this, we can derive the following. That the sine of theta, we can think of it as y over r, while the cosine of theta, we can think of it as x over r. Right? In other words, oftentimes this is referred to as the opposite. R is called a hypotenuse, and this is called the adjacent side over the hypotenuse. Right, so that's, we get opposite over adjacent from that guy. Okay, cool. We can define new trig functions. We can have something that's called a tangent. Right? This is defined to be the division of sine and cosine. Right? And hence, from the above definitions, we can figure out that that guy is going to be opposite over adjacent. Right? So that's one new trig function that we will define, called the tangent. And this, of course, this leads to the mnemonic that's called so, ka, to, ah. Right? So, ka, to. So we can know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So you have that. Some common triangles. Some such triangles are what we call the 3, 4, 5 triangle. If that's theta, we can say, for example, that cosine theta is going to be 3 over 5, sine of theta is going to be 4 over 5, while the tangent of theta is going to be 4 over 3, for example. So you can take the opposite sides of the guy directly across from that, the adjacent sides of the guy right beside it. Okay, so we have that. We can also talk about the graphs of sine and cosine. And these you are, of course, expected to know, and all the important points that they pass through. So if you have y is equal to cosine of x, and in general you could have gotten these by plotting points or something like that, but this actually does pass through some nice points here.
Quick note.
Yes.
On the 3, 4, 5 triangle, you switch to sine and cosine. Oh, sorry, the way you have it drawn, never mind.
The way I have it drawn, yeah,
Yeah.
the 3 and the 4 could actually swap places, and the same rule would apply. But yeah, so cosine would look like this. It is actually very important for you to know that when you're at 0, it hits 1. It hits 0 when you're at pi over 2. It'll hit minus 1 when you're at pi. It'll hit here 0 again at 3 pi over 2. It'll hit the peak again at 2 pi. This is called the principal period. The period equals 2 pi. This is called the principal period. Meaning, unless otherwise stated, this is kind of the period in which you would graph sine and cosine. It's important to know these values. It's also important to know that this exact same pattern repeats forever. Right? This gives us a few identities right away. Well, a few values of the trig function. We can know that cosine of 0 is 1. We can know that cosine pi over 2 is 0. We can know that cosine 3 pi over 2 is 0. We you know that cosine of pi is -1. We can know that cosine of 2 pi is actually +1. In general, we also want to know when cosine is 0. Cosine of x is equal to 0 means x is n times pi over 2, where n is odd. That's going to be an important thing to know. So if we're going to need to solve trig equations every now and then, and you need to know like when things hit 0 is going to be an important thing. So cosine equals 0 at every odd multiple of pi over 2. You'll see it here, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, etc., and going in the reverse. You also know that cosine is even. This would mean that you have this identity. Cosine of minus x is equal to cosine of x. Right? Because if you start to actually extend this graph, going back, you realize that any number you pick on this side, it gives you exactly the same y value as its corresponding negative on that side. Right? Because it's an even function. It's actually symmetric about the y-axis. Okay? So these are some important things to know about the cosine function. Right? And at any given time, you might have to apply one of these things. So it's important that they're, again, in the forefront of your mind. And so we can, if we look at y equals sine of x, we can kind of graph this guy. It starts at the origin and does that. 0. It will hit 1 at pi over 2. It'll hit here at pi, hit here at 3 pi over 2, hit here at 2 pi. So we can see here that sine of 0 is 0. We see that sine of pi is 0. We can see that sine of 2 pi is 0. In fact, in general, sine of x equals 0 means that your x has to be n pi, where n is an integer. Sine will be 0 at every multiple of pi, every integer multiple of pi. Sine of pi over 2, you should know is 1. Sine of 3 pi over 2, you should know is -1. You should also know that sine is an odd function. If we were to extend this graph, this pattern would repeat forever. If I pick a random number here and I get a y value, its negative will give me the negative of that y value. Sine is odd. This means that if you take sine of minus x, it's actually the negative of sine of x, for any x. There are some implications here. These graphs also imply the following. That if we take the integral from a to b of sine x dx, this will be 0. And integral from a to b of cosine x dx, this is also equal to 0 if ab is any interval of length 2 pi k, where k is a positive integer. So if you're integrating on any interval that has length 2 pi, so for example from 0 to 2 pi, or from 2 pi to 4 pi, or from pi to 7 pi, all of those guys, these integrals would automatically give you 0, so don't waste time actually computing them. They will work out. It's also true that because sine is odd, this also means that in general, if you're going from minus a to a of the sine function, that will always give you 0. That's also something you're not expected to compute, you just know that. And in general, you can say if you're going from minus a to a of the cosine, you can actually just double the value from 0 to a of the cosine. Because odd and even functions behave that way. So those are some implications to calculus for knowing these graphs. There are, of course, some special angles. These are angles I expect to actually know the value of sine and cosine. You can derive them from triangles by constructing cleverly constructing triangles like 3, 4, 5s, but you'll construct them where you have a 45 degree and a 60 degree and a 30 degree. Personally, I always found that difficult to remember, so there's actually a table with a strategy of how you can fill it out, and I kind of prefer to do it that way. And to me, I find it's easier in my head to figure out these angles by doing it that way. So you can think of your angle here as theta, this is sine theta, this is cosine theta. And these are the special angles. We have pi over 6, pi over 4, and pi over 3. This guy here is 30 degrees, this guy here is your 45 degrees, this guy here is your 60 degrees. Notice that 0 degrees, 90 degrees, and all that can actually come from this picture, so you don't have to memorize those. There is actually a larger table that I could do here, but I usually just, with the table and this graph combined, I know all the angles that I can be expected to know. So here's how you actually fill out this table. In the sine, you count from 1 to 3. You go backwards of cosine. You take the square root of everybody. And then you divide everyone by 2. And those are all the values of sines and cosines at those angles. Okay, so from this we can see, for example, that sine of pi over 4 is radical 2 over 2. Or I can say cosine of pi over 6 is radical 3 over 2, etc. Right? This table will give me all those nice angles. Now, there are some times when I have a multiple of one of these angles and I need to know the value. So just remember how to fill out this table. 1, 2, 3, 3, 2, 1, radical everybody, divide everyone by 2, and that gives you the angles. I think that's a lot easier to actually than drawing triangles and figuring out the numbers. And it's the kind of things where, because it has this strategy to it, you can visualize it in your head a lot more. You know, you can know, oh, 45 degrees, that's in the middle of the table, that's where the 2 is, it's radical 2 over 2, you know, so people ask you and you'll be able to say it almost right away. What about multiples of these angles? Well, one thing we have to remember is that all students take, correct? Right? So calculus, the PG version, right? This kind of says that unit circle will break into certain my black markers are dying. In the unit circle, we can think of quadrants here. This here is quadrant 1. And the quadrants are numbered counterclockwise. Alright, so the first quadrant, second quadrant, third quadrant, fourth quadrant. You can remember all students take calculus. And this is a mnemonic to remember the signs of certain trig functions, so that's one of them. So here this means all, A for all. All trig functions positive values. Right? And why that comes directly from the definition of sine and cosine, it gives you the x and y coordinate, and in this region, both the x and y coordinates are positive. Notice if you go to the second quadrant though, over here your x coordinate is negative, while your y coordinate is positive. So over here, you will have the sine is positive. You'll also have the cosecant is positive, right? Because sine and cosecant is the same. All others negative. Here you will have the tangent is positive. Because tangent is sine over cosine, they're both negative here, so if I divide a negative by a negative, I get a positive. So tangent is positive, hence cotangent is positive. All others negative. Over here, the cosine is positive, because the cosine is the x, but of course the sine is negative, and if the cosine is positive, so is the secant. All others negative. Right, so all student state calculus can talk about the signs, and where cosecant x is just the reciprocal of sine, not to be confused with the inverse of sine. Secant of x is the reciprocal of the cosine, and cotangent x is the reciprocal of tangent. So that's the first thing you need to know. The second thing you need to know is dissecting. Hope I spelled that right. Dissecting the circle. Conveniently based on the special angles that are over here. So we can see an example. For example, let's say we needed to compute sine of 5 pi over 6, right? So not pi over 6, but 5 pi's over 6, right? What you would look at is you kind of focus on the part of this that's the special angle, namely the pi over 6, right? It turns out the answer to sine of something like that, if it doesn't reduce to get like one of the other special angles from the graph, something like this will behave like, it will behave exactly like pi over 6 because of how the circle is. The values start repeating after a while, except it might be a plus or a minus. And this depends on the quadrant. Right? How does it depend on the quadrant? By this rule. So, for example, if you see what is sine of 5 pi over 6, what you're going to think of it is the following. Here's where the angle 0 is, here's where the angle pi is, that's 180 degrees. And so what you're going to do is you're going to divide pi into 6 pieces. Right? Because you're taking pi divided by 6. So this means you divide the pi into a half, and then each half into 3 parts. You can do that at the bottom, because it might be appropriate. And so now what you do is you take 5 pieces. So each piece here is worth pi over 6. You want 5 pi's over 6, so you start here and you count them off. 1, 2, 3, 4, 5. Boom. That brings you here, that puts you in the second quadrant. And so I know that sine is positive in the second quadrant. So that would mean that sine of 5 pi over 6 is just going to be positive sine of pi over 6, which is going to be, from that, we know that's going to be 1/2. Let's do a similar example. What if I had to do cosine of 5 pi over 4? Well, again, I'm going to if not directly drawing this, I'm going to visualize this in my head. Take pi, divide that into 4 sections. 1, 2, 3, 4. You can do that at the same time here. Now you want to take 5 of those sections. 1, 2, 3, 4, 5. It brings you here in the third quadrant, so I know that cosine of 5 pi over 4 is going to be equal to, in the third quadrant, my cosine is negative, so it's going to be negative the cosine of pi over 4. By that table, I know that that's radical 2 over 2. So the special angles, they'll give you similar values in absolute value as the table, but the signs might change depending on which quadrant the special angle ends up in. To figure out what quadrant the special angle ends up in, you dissect this into the denominator. Just dissect pi into as many pieces as the denominator, and you literally count off the pizza slices to figure out where you are. And that method works because of reference angles and things like that. Because the angles that are closest to the x-axis, they'll all be the same magnitude. So, because the circle revolves on itself, the values repeat. And the only thing that will change is the sign depending on where you are, and that goes based on this rule. So that tells you how to find the values of the trig functions at special angles. And multiples of special angles that aren't 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay. What do I need to remind you of? Okay, so I define sine, cosine, graph this. Define that. Cosine even not, I already said that. Okay, I'll end with graph and transformations, but more Pythagorean identities. So we know that cosine squared plus sine squared equals 1. This would mean if we divide by, say, cosine squared, what I would get, this divided by itself is going to be 1, plus sine divided by cosine is tangent, and 1 over cosine squared is going to be secant squared. This is a very important identity. This is just another formulation of the Pythagorean identity if we divide by cosine squared. You can also divide by sine squared. And so this would give us cosine divided by sine would just give us cotangent. That would be 1. And this divided by sine would be cosecant squared. When doing integrals of trig functions, those guys will come in handy. Also, there's things called the addition formulas that you'll need to remember. So basically the proof is this. You can take a right triangle here, call this angle A, where it has that. You can stuff it right on top of another right triangle, call this B. Right? You can sort of construct another right triangle here, and you give these guys names, length A, B, C, D, or whatever. You can figure out the side lengths of these guys by using Pythagorean theorem and all that to create a bunch of right triangles. And you can actually use that to derive these identities. I'm not going to do it because I would assume that it's been done for you before, but we can, from this, obtain the following. That if I take the sine of A plus or minus B, this gives me sine of A cosine of B plus or minus sine of B cosine of A. Right? And you can use SOHCAHTOA and just play around with these triangles and get that identity. We can also get that the cosine of A plus or minus B is actually going to be the cosine sine. Cosine A, cosine B. The signs for the cosine will change. So if it's a plus here, it's a minus here. And then it's sine sine. Sine A, sine B. So those are the addition formulas. From this we can get what's called the double angle formulas. Note in particular that I can think of something like 2x as just x plus x, right? And then I can think of x and x as the a and the b. And so this would give me that the sine of 2x is, if I apply this formula, plugging in x and x for the a and the b, I would get 2 sine x cosine x. Also note that the cosine of 2x, if I plug in x and x here, I would get cosine squared of x minus sine squared of x. Notice I can also rewrite this. I can write this as 2 cosine squared x minus 1, or I can write this as 1 minus 2 sine squared x. And these are by applying the Pythagorean identities. Here, I substitute sine squared x equals 1 minus cosine squared x into this formula, and I would get that formula. Here, I can substitute cosine squared x equals 1 minus sine squared x into this formula, and I will end up with this one. You should know all the variations of cosine of 2x. Yes?
That last formula, is that plus or minus sine A, sine B?
No, this just, what this means is that if I have cosine of A plus B, then it's cosine of A, cosine of B minus sine A, sine B.
Oh, okay.
And if it's cosine of A minus B, then it's cosine of A, cosine of B plus sine A, sine B.
Okay.
Right, so writing plus minus versus minus plus means that when this takes a plus, that takes a minus. When this takes a minus, that takes a plus. You can actually show that it swaps the sign. The sign is in SIGN. So another thing that comes out of this is the half angle formulas. So this is basically us kind of working around these guys so that we can say sine squared of x is equal to 1 minus cosine 2x all over 2 by solving this guy first, sine squared. And cosine squared x is equal to 1 plus cosine 2x all over 2. Did you guys learn how to integrate sine squared and cosine squared in Calc 1? Did you guys learn that? Do you remember? Like if you had the integral of sine squared, would you know how to do that? Well, this is how you would do it. You would rewrite this as that, and then this is just an easy substitution. U equals 2x, and then you just integrate cosine of u. Okay. So this is one example of why all these formulas I'm regurgitating to you are important, because you're going to get things that we're raising things to powers, and it's going to be a complicated mess. But a lot of times knowing these formulas can get you out of the woods. By just rewriting something, it goes from, I'm not sure how to deal with that, to, oh yeah, just do there. This is easy to integrate. That's kind of, I don't know. So yes, the addition formulas, the double angle formulas, and the half angle formulas are very, very important for you to remember. In particular, when it comes to integration, we're going to use those all the time. There's one other set of things I need to tell you, but we'll leave that for next time. So we'll talk about graphing some crazy trig functions. So for example, if you're given something like 2 sine of x plus pi over 4 minus 2 or something, how would the graph of that look like? An easy way to get to the graph of that. Because later when we do polar coordinates, knowing how to do that is going to be very important. So we'll talk about that next time, and then we'll actually start talking about the inverse trig functions, since you know about trig functions. We'll talk about their inverses and calculus of the inverse. See you guys on Friday.